Hi, everyone. Thank you so much for your patience and also for joining us today. So incredible but true, we are 5 minutes late with the schedule, so Swiss time is not functioning perfectly. You saw there was a bit of confusion with lunch, but thanks everyone for making it happen today. So we have a rather big program today. Exciting set of speakers, exciting set of talks for launching the Pilatus4 detector. So you will see here, there is quite a lot to do with the technical specs of the detector from Tilman and Marcus for Synchrotron and Laboratories. And then we will also hear about how these machines are applied and what do they actually bring in use at synchrotron sources and in laboratories. Now, to make everything in a bit of a better context, Pilatus is our maybe favorite child, or maybe best known child of DECTRIS. So Clemens will put all of this in context and tell you a little bit about history and how this really worked out. Probably you will have really lots of questions. We won't be able to answer them now at the lunchtime seminar, but we will be down there at the booth number 10. So it will be plenty of time to ask questions, discuss, and also to pick up your tiny little present, your tiny little souvenir after this seminar. So in any case, even if you have questions or not, see us at the booth 10 after the seminar. And then with this, please, I will invite Clemens to tell us lots of beautiful stories and history of Pilatus.
Can you hear me? Yes. Excellent. Okay, that worked. Thank you, Dubravka, for the introduction, and thank you for joining our lunchtime seminar. It's great to be here. And okay, yeah. So to answer the question why I will give this presentation, well, the simple reason is that our founder and president, Christian Brönnimann, couldn't make it. But there's a more profound reason, is that this detector, the Pilatus, our favorite child, is very close to my heart. And it has been since many, many years. But I had to be very, very patient. And I will tell you more about this afterwards. Because first, I would like to introduce our new product manager, synchrotron radiation, Sasha Grimm. Actually, Sasha doesn't need much of an introduction, because many of you will know him from the commissionings, from training, from the rare cases when the detector doesn't work properly, or the software or the firmware. But Sasha has started his career at DECTRIS as a field system engineer in support, and since 5 years he has been building the global support team. It's a small team, but very dedicated and very efficient. Sasha loves to talk to our users, and he will translate your needs in the application into specifications for new products that will enable you to do even better research. So come to our booth and talk to him during the conference. So why do we present Pilatus4 today and to launch it? For this, I would like to go back 25 years in time to a small village in Switzerland, to the Paul Scherrer Institute. And 25 years ago, X-ray research was severely detector limited. And the Paul Scherrer Institute just got the approval in 1997 to build the Swiss light source. So the management of Paul Scherrer Institute had a vision. They wanted to apply the technology that was being developed for the CERN, for high energy physics, to develop a detector for X-ray experiments. And they set a very ambitious goal They said they wanted a detector for protein crystallography as big as 40 by 40 centimeter, and they even set the date. They said, this will work on Swiss National Day, August 1st, 2001. Okay. And maybe some of you know, but most of you won't know, Pilatus has a meaning. It means pixelated apparatus for the SLS. Yeah. So good. So August 1st, 2001 came, and there was no Pilatus detector at the beamline. We had to wait until November 2003, and then the Pilatus 1M finally made it to the beamline. It was the largest hybrid photon-counting detectors at the time, 24 by 21 centimeter, not quite the 40 by 40. Well, these are the original slides. There were 10% defective pixel that you see here, and Armin Wagner, who just came in, he had the wonderful task to process and the canonical lysozyme data, and well, I mean, he was really struggling with it. With all the defective pixel and the wonderful Tyndall geometry that was introduced with this detector. And in the end, I think it was more the power of molecular replacement that saved him and not the quality of the data. So, but anyway, the story got written up in Journal of Synchrotron Radiation, and this wonderful detector went straight into the museum. So, and it took another 4 years before the first Pilatus detector was born. So this is the Pilatus 6M, which in 2007 came to the beamline X06SA, and this time it worked. So technically speaking, it's a Pilatus 2. And what you see here is really the first prototype. It has an area of 45 by 45 centimeters or something, and 6 million pixel, and approximately the dimension of the minibar in your hotel room. Many people came to the SLS to test this detector, and Venki Ramakrishnan was very interested in using our beamline because we had promised him a kappa goniometer and a pixel detector. And well, the kappa goniometer only came years later, but he still wanted to test his 30S crystals because he was reckoning that the low musicity of his crystals would provide very small diffraction spots with a direct detection detector. And he wasn't disappointed. So today this may be a standard, but at the time this was really stunning to have this really well confined and small diffraction spots. So such a large unit cell with so nicely separated spots. And so since then, the Pilatus detector has unleashed the power of third-generation synchrotron sources, or contributed to it. The community which picked up Pilatus and hybrid photon counting detectors quickest was the protein crystallography community, and the Pilatus really contributed to the transformation of protein crystallography during the last 15 years. And this is still ongoing today, from cryogenic undulators to machine learning assisted phasing. So there's a huge stimulation of detector and other instrumentation. We like to listen to our users, and in the 2011 IUCr Congress in Madrid, the Diamond folks came and said, we need a much faster detector. Pilatus is great, but we need a much faster detector. And then there was a small molecule crystallography. We need higher count rate capabilities. And I guess also the material scientists, they were kind of jealous and said, oh, we need a detector which has higher quantum efficiency at high energies. And we put all this together. And in 2013, we started to ship Pilatus4, the first detector that was fully developed by DECTRIS, developed and produced by DECTRIS, and also compatible with cadmium telluride sensors, high-Z sensors. And this detector, the Pilatus4, has really become the workhorse around synchrotrons around the world. And it's been used for macroelectric crystallography, small angle scattering, for surface diffraction, and many other applications, including imaging. But it also established hybrid photon counting in the laboratory, because Rigaku had asked us to design a 200K, the Pilatus4 asked 200K, and that became really very popular. And basically since then, I think this is a established technology in the laboratory as well. But what you see here is neither of this application. What you see is an application that was only made possible by this detector technology, the high-Z sensor Pilatus4, cadmium telluride. So that is X-ray diffraction computed tomography. And this technique has been pioneered at ESRF and the finance company, but it only lived up to its expectation once these detectors became available. And Stefano will report on the latest results obtained with the Pilatus4. So, and this finance company got recently awarded the Sir George Stokes Prize for the advancement of X-ray diffraction computed tomography, because this technique allows to study functional materials under operational conditions, so in situ and operando studies of real-life devices such as batteries, fuel cells, or catalytic cells. And this is obviously technologically extremely relevant. This summarizes pretty much what Pilatus has done in the synchrotron community. It really transformed the way the X-rays have been detected, and it's something that with an image plate or CCD was hardly imaginable. And this transformation goes on. The synchrotron community keeps improving their sources. So over the last 35 years, synchrotron brilliance or brightness has increased by 9 orders of magnitude. And the upgrade from the third to the fourth generation brought 2 orders of magnitude in brilliance. So some people, like Henry Chapman, argue that you need integrating detectors to cope with this brightness, and that they would be a great match for the upgraded synchrotrons. But we at DECTRIS think that the Pilatus4 is a very good match for modern synchrotrons. And we have developed this detector for this community, for the X-ray crystallography community. It's a Pilatus4. It has 4 energy thresholds. It can operate at 4 kilohertz at a full size of 4 megapixel. And it's the Pilatus4 for you. Thank you.
Yes, so welcome also from me. My name is Tilman. I'm product manager at DECTRIS and responsible for the Pilatus4 detector. And Clemens already spoiled all the main features of the Pilatus4, which are also summarized here, before I even started my presentation. So Yeah, Pilatus4 is here. It's the next generation of the Pilatus, following the very successful Pilatus3. And as you can see, it's real. It's standing here. This is one of them. If you cannot see it now, you can also take a look at it later on at our booth. You're very much invited. We decided to make a new upgraded Pilatus4 with the latest hybrid photon counting technology, and I'm now going to show you what really is inside the detector. So Pilatus4, Clemens mentioned, it's developed for the synchrotron, and there it delivers high efficiency, and it's a large area detector for fast data collection. But it will also be available for laboratories. And this is what Markus is going to present to you in his part. In more detail, I'm going to focus on the synchrotron. And now you might recognize this eventual copy-paste error for laboratories. It's also a high-efficiency detector with large area for fast data collection. But it's no copy-paste error, it's on purpose, right? So obviously, for the synchrotron, large is a bit larger and fast is quite a bit faster. So what is it for the, I now go to the synchrotron detectors. They are large and fast. So the one that's standing here, that is the 1M detector. That is the smallest we will deliver for the synchrotron, with a 150 times 160 millimeter active area. And then it goes all the way up to the 4M detector, the largest, with double size in both dimensions. And the really cool thing about these detectors is that they can run at 2,000 frames per second. Even the largest detector can run at that speed. And not only that, but they also offer an 8-bit mode, so you can reduce the bit depths to 8-bit and then speed them up to 4,000 Hertz. And moreover, like for the Pilatus3, we will offer cadmium telluride and silicon sensors, starting with the cadmium telluride 1 deliveries supposed to start in Q3 2024. So now comparing the Pilatus4 and what advantages it brings relative to the Pilatus3. On the left side, the Pilatus4 will have a slightly reduced pixel size of 150 micron. We stay with this moderate pixel size for a good reason, because this allows really to reach this speed at the large active areas, so the 4,000 Hertz. This comes also now with continuous readout. I will show you what that means, and it gets rid of the readout time that you had on Pilatus, and it really allows you to go fast. Oops, sorry. And then this is also possible because we adapted the Simplon control interface from the IUCr detectors that is well established and offers this fast streaming. And there's a very important new feature. We now have 4 thresholds available on Pilatus4. So you can not only discriminate noise and leakage current and potentially fluorescence as you could on Pilatus, but you can also remove higher harmonic signals, and you can think what else to do with these additional thresholds. There's an additional double gating mode that allows in pump probe measurements, you can record 2 different time delays over the same exposure sequence. Yeah, and then there is the detector is fully calibrated as you're used to from DECTRIS detectors, and offers all the hybrid photon counting advantages that you know. So what is really the electronics in the pixels that enables this? Here is a little simplified scheme shown. What you can see is we have these 4 parallel thresholding stages, starting with these comparators, where you can set 4 independent thresholds. And then in each of them, there's the re-trigger unit, which enables non-parallelizable counting. And this allows us, with this detector, to go to above 10 million counts per second in each pixel. Yes, and then the very nice feature here is that each of the threshold circuits also has 2 counters at the end. And this is used in a fashion to enable continuous readout. And this is animated here. You can see what happens there. So while one counter is receiving the signals for counting, the other counter can be read out. So in this manner, you have a detector that is always active. And the gap between switching these counters is only 100 nanoseconds. By that, you're almost 100% of the time counting and efficient. So we had the pleasure, that was the best part of the project, I must say, to take a prototype cadmium telluride Pilatus4 detector to 3 synchrotron beamlines. And I'm going to present to you one example, mainly from Spring 8, maybe shortly the one from Max 4, and then Stefano is going to show in more detail the measurements that have been performed at ESRF. We focused here, I should say, on high energy powder diffraction because we think the Pilatus4 is an especially good match for that, also for other applications, obviously, but with the high quantum efficiency of the cadmium telluride sensor and the large active area, it allows you to collect a lot of signal from powder patterns and really make use of the high speed as well. So the test at Spring 8 was performed by a user group from Osaka University, and they were investigating in situ spot welding in an industrial spot welding setup and doing this at 1,000 frames per second, running the beamline at 100 keV to penetrate these metal samples that they were welding, and at a very high photon flux of 10 to the 13 photons per second. And what they then could observe and find, they were happy that they could time resolved see the phase transition in this spot welding region. Just a short also look at what we did at Max 4. Just one experiment we did there was running the detector really at 4 kilohertz. This you can see here. It's 500 milliseconds of in total a much longer 15-second sequence that was recorded that has the relevant part. Well, both of this is possible also because you have the efficient detector, and you will even have a larger detector that makes you go even faster and get a lot of signal. With this, I'm already at the end of my presentation. I invite you to come to the booth. And now hand over to Stefano for the results from the ESRF. Thank you.
Thank you very much. Thank you, DECTRIS, for having me here. Thank you for the birthday present. I'm going to show a few results from the use of Pilatus3 at RE15A over the last few years. Show some examples where it really made a difference, which kind of experiments it really made a difference, and where the Pilatus4 can potentially even improve on the advancement of the Pilatus3. So everything started in October 2016 with one of the first Pilatus3 prototypes delivered to RE15A. And then early 17, the Pilatus3 still in use was installed. This is what it looks like these days, on a permanent mount. And then earlier this year, there was the Pilatus4 prototype used. Oh, yeah. And RE15A is a beamline delivering 10 to the 12th and the 13th photons per second over a range of 40 to 120 keV, which means the main advantage of the Pilatus3 was the cadmium telluride sensor, which makes it very efficient over the whole energy range. Then if you look at the range of techniques of RE15A, you can see the photon-counting detector is a very good match because it can really offer an advantage in all of them. So the first test is what Clemens already showed. Superconducting wire. There's a weakly scattering niobium-3 tin in a tungsten tube. And you can see in the Pilatus image that you can get all the powder rings up to moderate Q, even in the presence of the strong reflection from tungsten, which are actually orders of magnitude stronger. And having a very high dynamic range could be used for pair distribution function analysis in difficult conditions. One example is trying to measure PDF in a diamond anvil cell. So what you got here is very strong reflections from the diamonds, hundreds of times more intense than the actual useful scattering from, for example, a glass or a liquid. But with a high dynamic range, you can keep both signals in the linear range of the Pilatus, strip away the Bragg peaks, and get a smooth signal from, in this case, water, and get the PDF afterwards for analysis. Speaking of PDF, the typical experiment is operando catalysis, which involves a very long time series. More on the catalysis part this Friday. There's a talk by Daniela. But what's important here is that you can use the energy cutoff and a zero background to get very clean signal in high Q, which is critical for PDF. and you can collect a long series of images over several minutes without using the shutter. And then after the SRF upgrade in 2020, the photons are enough to collect a good PDF in 1 second on a 5% loaded catalyst. And you can see that it's quite sensitive to the nucleating species in and around the nanoparticles. The high frame rate is also used for more material science-based experiments, especially combined with the triggering and gating capabilities. There are two main series of experiments where a series of images is connected to the manipulation of the sample. So irreversible processes can go through a fast full-speed burst of images. In this case, the electric field was switched on a PZT ferroelectric, and you can record the strain as a function of time and the azimuth on the detector to get the mechanism of polarization switching. For processes that are too fast for a single burst, for example, ultrasound 20 kilohertz stress pulse on a nickel titanium alloy, you can use what they call the stroboscopic mode. So the process is reversible. You can pump the sample as many times as you can, and then you slice the process into time channels. So in this case, a 1 microsecond slice was used to characterize strain along the 20 kilohertz oscillation in the alloy. Gating is also the mechanism behind linear scans, where you want to relate positions within the sample to a series of images. So most usual application today is batteries. So you can scan a coin cell across the depth of the graphite anode, record images. In this case, half a second was enough to go up and down a 100 micron electrode. And you can look at where lithium goes in space and time as a function of the state of charge. And this is just a one-dimensional example. If you want to go over more dimensions, you can collect tomography. Tomography is usually collected by continuously spinning the sample while scanning along the horizontal axis. Each projection is integrated into a diffraction pattern, powder diffraction pattern, which is then merged into sinograms rather than transformed into reconstructions, which are really two-dimensional slices of the sample, each pixel containing a powder pattern which I analyze like a conventional diffraction pattern. And the number of projections and how long it takes to collect a tomogram is really a function of the sample and what you want to see in the sample. So there are cases where you want to go in on the resolution, which means it will take 20 minutes to collect a slice, but then you can really get subparticle information. So in this case, one secondary particle from a battery cathode had several tens of diffraction patterns in it. The opposite example is a large battery, like an 18 millimeter battery, which is measured during fast charge. Fast charge means a full charge in 10 to 15 minutes. And because it's a large sample, one has to find the best compromise between going fast and getting enough resolution. So with a 200 micron pixel, 3-minute slice, you can still get the internal winding with the electrodes and the current collector, which was then used to measure temperature inside the battery while cycling. And this is actually the first example I'm showing with the Pilatus4, so comparing the 200 hertz and the 4 kilohertz measurement of the same battery, and then showing something about diffuse scattering, which is where the zero readout time really makes a difference. That's what it looks like, 4,000 hertz. You can really push the spatial resolution here. It's a factor of 8 improvement, I think. And you can see how now you got many pixels describing one period of the electrode. And it's even much easier to find defective parts of the battery by looking for a specific phase, because it will not be mixed with other features of the battery. And I think one of the first few articles on the Pilatus3 was about diffuse scattering, and then essentially not having a readout time allows you to do even finer slicing of the angular space, which means less dead angle. And this allows avoiding saturation, and it makes usually cleaner images with fewer dead, fewer unusable pixels. There are, of course, other more applications. There are some photon-hungry techniques, and you can read it for yourself.
Hi, I'm Markus Müller. Thanks for joining our lunchtime seminar in Pilatus4 product launch. You've just heard from Tilman about the outstanding features and specifications of Pilatus4, and Stefano has shown you amazing examples of what you can do with Pilatus4 at a synchrotron beamline, and you might be wondering, can I get Pilatus4 also for my lab, and how is it different from the synchrotron detectors? And the answers are yes, you can, and it's basically the same detectors that only differ in the available area and the maximum frame rates. For laboratory, we offer two square-shaped geometries with about 8 by 8 and 16 by 16 centimeters, and also a wide geometry that is more targeted towards imaging applications, but that can also be very useful to cover a wide 2 theta range. And with 100 Hertz maximum frame rate for the 260K models and 10 Hertz for the 1M, you have more than enough frame rate for anything you want to do in your laboratory. So what are the key features and benefits for laboratory applications of Pilatus4 cadmium telluride? First, the large area of up to about 16 by 16 centimeters, which achieves a wide coverage and gives you efficient data collection. The detectors also feature superior count rates and continuous readout, and this enables 10 orders of magnitude dynamic range and highly accurate strong intensities without overloads. And of course, the key benefits come from the direct detection in the cadmium telluride sensor, the sharp point spread function, and a small parallax that improves peak-to-peak and peak-to-background separation and gives you better data quality. And the cadmium telluride sensor also enables universal detectors for any radiation from copper all the way to short wavelengths of silver and indium. And this gives you up to 2 times higher quantum efficiency compared to the 1 millimeter silicon sensor of Pilatus3 for faster data acquisition. So I've mentioned the small parallax that can be achieved with cadmium telluride, and to illustrate that, I'd like to use the attenuation length, which is the distance into the sensor where the intensity has dropped to 1 over E, or about 37%, which means that at the attenuation length L, 63% of the intensity was absorbed in your sensor. And here we see the attenuation length for molybdenum and silver radiation, for silicon and cadmium telluride, and you see that cadmium telluride has more than 10 times shorter, 10 times better attenuation length compared to silicon. So what happens in a silicon sensor with perpendicular incidence is you have poor efficiency because the attenuation length is larger than the thickness of your sensor, and at shallow incidence you suffer from large parallax and your intensities get distributed over many pixels. So large parallax gives you more overlap of peak and background and also potential overlaps of spots. Whereas with the short attenuation lengths in cadmium telluride, the parallax is extremely small. You get better peak-to-background separation and excellent spot separation. Most important property of the cadmium telluride sensor material is the high quantum efficiency. With the Pilatus4 cadmium telluride, you have more than 95% quantum efficiency for any radiation from copper to silver and indium. Compared to Pilatus3 1 millimeter silicon, you have similar quantum efficiency for copper and 2 times higher quantum efficiency for silver and indium. So Pilatus4 cadmium telluride, you don't need to compromise in a dual wavelength setup, and you have high quantum efficiency and fast data acquisition for short wavelengths. Pilatus4 cadmium telluride is available directly from DECTRIS and also from our OEM partner STOE. Stay tuned for other OEM partners. You can ask for a demo or a loan system now, and the detectors will start shipping in about a year from now in Q3 24. So I'd like to summarize. Pilatus4 cadmium telluride offers large area up to 16 by 16 centimeters, direct detection in a cadmium telluride sensor for extremely small parallax, and universal detectors with more than 95% quantum efficiency for any radiation from copper to indium. So Pilatus4 gives you high efficiency and large area for fast data collection. And how you use that in a lab setup, Laura from STOE will now show you.
All right, thank you very much for that introduction. So yes, I'm Laura from STOE, and I'll show you a little bit what we've done so far within our lab. So first of all, for the ones who don't know our company, I just want to give a quick introduction. So we've been originally founded in 1887, originally to do exterior analysis of crystals, and later on, after Bragg and Laue, etc., did their research, we started manufacturing single crystal diffractometers and powder diffractometers. We are very well known for our transmission geometry in powder diffraction. Nowadays we have the first area detector system, the IPDS, and our STADIVARI, which is the system on which we have implemented the Pilatus4. So we have quite a long history with DECTRIS as well, since 2009, when we got our hands on a Pilatus for the first time. And here you just see a picture of where one of my colleagues was starting to implement this Pilatus on our STADIVARI. Since then, we had the chance to work with the Pilatus3 cadmium telluride, the IUCr cadmium telluride, and since this year, also the Pilatus4. And here you see the STADIVARI. This is the instrument on which we did this implementation. So this is our four-circle goniometer with a Eulerian cradle. As you see here, it has a sphere of confusion of less than 5 microns. We have various types of sources, and nowadays it's very often that users like to have 2 sources in one instrument. So for example, one source with hard radiation, one source with soft radiation. And then the ultra-fast hybrid pixel detectors, mostly from DECTRIS, as we see. And here we go now into the measurement that we have been doing. So we have compared a Pilatus3 silicon sensor detector to a Pilatus4 cadmium telluride detector. We used for both measurements nickel selene as a sample. You see it here. Detector distance of 100 millimeters, 1 second exposure time for copper measurements, and 60 seconds exposure time for silver measurements. So if we look first at the silver measurements, we see what is most important is that we get a quite higher I over sigma in the different measurements compared from Pilatus3 to Pilatus4. And if we look at single reflections, we see also here that the intensity is much higher in the cadmium telluride Pilatus4. And here you have some examples also for peak shapes. If we look at copper radiation, we see that we do not really lose any very much intensity of reflections all over, going from a silicon sensor to a cadmium telluride sensor, which so far might have been a bit of a problem. Also, if we look at the respective single reflections and their intensity, we also see here that there is not much of a loss. So this is really the excellence of this Pilatus4 detector. We also did some comparisons because conveniently on our STADIVARI diffractometer you can also do some powder diffraction. And we used LAB6, the standard we usually use, with a detector distance of 130 millimeters and an irradiation time of 60 seconds. And you see already the comparison Pilatus3 to Pilatus4, so you have much more intense powder rings here on the Pilatus4. And what is also really convenient is you really just have one module gap. So when transforming this to the one-dimensional powder pattern, you have less area that is not usable, so to say. And if you look at it in the powder pattern again, you see also here you get much more intensity for the Pilatus4. And with this, I already come to my conclusions. So you have the same great performance for copper in the Pilatus4 as with Pilatus3. but you get better data for hard radiation, or you get shorter measurement time. So this is really excellent for systems where you have two wavelengths, one with softer radiation, one with harder radiation, and you have an optimal detector for both of them. So this is really the universal detector for these kinds of instruments. And with that, I would like to thank all of you for listening. Thank you, DECTRIS, for having me. And if you have any more questions to STOE, please visit us at stand 36. Thank you.
Thanks, everyone. Thanks, Laura. Thanks to all speakers. We started a little bit late, but there are still two huge announcements to make. One is Pilatus 1234 was developed for the community, with the community, and it is, as we say, probably our most favorite child, our favorite detector around. So we invite you to come and join to our booth to pick up your little Pilatus souvenir. So we have here specially designed T-shirts with the Pilatus on it. So for all Pilatus fans, just drop by and get your T-shirt. And before you leave, please, just one huge applause and all the best to Sasha and Stefano, who are celebrating their birthday today. We wish them lots of photons and all the best. Thank you very much. Thank you.
Thank you.